Hey guys, welcome back to my video, and in this video I'll be talking about quantum solutions, specifically focusing on cybersecurity and PQC. This course hinges on the MIT X Pro Advanced course on quantum algorithms, which specifically focuses on cybersecurity, PQC, chemistry, and optimization. Today we are doing cryptography and data security, RSA encryption, post-quantum cryptography, the quantum Fourier transform and Shor's algorithm, and also some coding, and the quantum threat and the solution to it. So let's break down the standard model of communication. So let's say one guy, Alice, wants to send a message to another person, Bob. But the channel is public. It's like shouting across a room full of people. Everybody will hear you. So you can't send a secret message. But if they want to send a secret message, well, how will they do it? So for that, Alice will encrypt the data. So this is what encrypted data looks like. You can see here, it just looks like blah, 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 but it actually has a message inside. Security doesn't come from hiding the communication. It comes from hiding the information. But now that Alice has encrypted the data, how will Bob decrypt it? Bob will think it's just a random keyboard, cat on keyboard smashing all the keys. So for that, we use a cryptographic scheme. So we have symmetric encryption, asymmetric encryption, hybrid encryption, hash-based protection. Hash-based protection is used for password storing, so we're not going to deal with that today. And then we have post-quantum cryptography. Post-quantum cryptography I will do after Shor's algorithm, or you can say post-Shor's algorithm. I'm just joking. After Shor's algorithm, when I show here, I will show. Okay. So now let's start with symmetric encryption. Symmetric encryption uses one shared key for both encryption and decryption. So encryption, you use the key ding dong, I guess, and that would be a very bad key, but let's say you used a key, you would randomly generate it and then you would share it privately, and then on the other end you can use the same key for decryption. So Alice and Bob need to have the same key, but if anybody else gets that key, they can decrypt, right? So you need to share that key privately. So how do we avoid this obligation to share a secret key? Well, for that, we use something called asymmetric encryption. It uses two keys, one which is private, one which is public. The public one encrypts, the private one decrypts. So it's like anybody can lock, but only you can unlock because you have the private key. So you send the public key to the public, anybody can lock the message, send it over to you, and then you can unlock it using the private key. So then we have, and some examples include RSA and elliptic curve cryptography. This is what makes communication over the internet possible. But unlike symmetric encryption, which is fast and power efficient, this one is not as fast and power efficient. So how do we not share the key and have it fast and power efficient? Well, for that, we use hybrid encryption. In hybrid encryption, we combine both symmetric and asymmetric. So we use the asymmetric as a private channel for the symmetric key, and then the symmetric handles the actual data. So you can see we encrypt using asymmetric the symmetric key. Now that we have encrypted the symmetric key, we send it over. Now the symmetric, we can actually use the symmetric key for symmetric data. Not symmetric data, the data will actually be handled by symmetric encryption. And this is very suitable. So it's used everywhere, WhatsApp, HTTPS, cloud security, everywhere. But are there any downsides? Not yet. But quantum computers can break RSA. Now that RSA is like, how does a classical computer not break RSA, but a quantum computer does? For that, we first must understand the fundamentals of RSA. So let's do it. So this is how RSA works at a high level, not a low level, from a high level. So a message gets converted into numbers. Message into numbers, so you get high into 6 plus some random string of numbers. Next, you encrypt it using the public key. The public key is made out of two numbers, E and N, and then it's sent over the channel, decrypted using the public key, which is also made of two numbers, D and N. Next, we convert it back into letters. So now let's get into what the public key and private key are. So n is equal to p times q, and p and q are both prime. Since it's a multiplication of two primes, we call it a semi-prime. Yeah, it's a semi-prime. Now what we do, we find a number which is the private key d. But before that, we must find what e is. You can see e here. And for e, that's part of the public key, e and n. And e you have to choose. And it's a number you need to choose between 3 and n minus 1. And the GCD, or the greatest common divisor, of e and r has to equal 1. Otherwise, you have not to do that. So GCD of e and r has to equal 1. Now we know what e is. We do. D is equal to e inverse mod r. Now you may be thinking, oh, what's this fancy pantsy mod function? So I will go up to the board and explain what the mod function does. So now that I'm on the board, mod is basically just a remainder function. So if I make this black, so it'll actually, you can see what I'm writing. Yeah. Mod is a remainder function. All it does, it's just like if I have 32 mod 5, what I do, 32, 5, 6, 32. Answer is 2. It's pretty simple. So it's just remainder. You can also just check it by 32 minus 2 should be divisible by 5. And 30 is divisible by 5. So that's also another way to check it. So that's what mod is. Remainder function. Kind of simple. So now we know what mod function does, and we know d. D is e inverse mod r. So then we can encrypt and decrypt the message using this, and I have wrote some Python code for this, so we don't need to do everything by hand. So Python code time. Wahoo! So this is the basic RSA demo. You can see here. If I run this, it'll ask to input right here. So it'll ask yes, enter modulus or n. So let's say I want to take 33, just like I did. So then r would be 20, because n minus 1 into q minus 1 into n minus 1. So that would be 3 minus 1 and 11 minus 1, so it'll be 20. So the GCD of the number which I enter and 20 has to equal 1. So I'll choose 7. Boom, it generated everything for me. So 3, 11, so r is equal to 20, e is equal to 3, which we put, and then e is equal to 7, and then we get d is equal to 3. Now we can encrypt a message using the encrypted message, or we call ciphertext. Also, all of this code is available for free on GitHub. I will put the link in the description. So we call encrypted messages ciphertext. So ciphertext is the encrypted message is the message to the power of e mod n. So if I do that, let's say I want to encrypt the number, I do not know, 23. Oh my gosh, I picked one of the lucky ones. Let's say I need to encrypt the number 15, and the encrypted message is 27. Now if I decrypt 27, I get 15. Yahoo! It works. Okay. And also I can do the mod function by doing pow. So if I have a mod b, I do, because pow, what it does is a to the power of b mod c. So if I do 32 to the power of 1 mod 5, I should get 2, and I get 2. You can see here I did the same thing. 32 mod 5 is equal to 2. So that's basic RSA. Now let's go back. Now we know that if we take n and factor it into p and q, we know d, so we can read any message if we factor it. So I have this factoring algorithm over here. So what if we factor an RSA number? RSA you can break easily, right? But there's a catch. There's not a throw. No, don't throw. There's a catch. So when you actually do it, On a classical computer, it's stuck. It just gets stuck. It takes way too long. And you can see here, it actually takes, this is the number of operations. Actually, I'll stand up. So this is the number of operations, and that is and the bottom, this side is RSA key size. This is number of operations, and this is on a log scale. So you can see here, usually what the standard is, RSA 2048, sometimes they use 4000, sometimes basically they use from this to this range. And from here you can see you need to do 10 to the power of almost 42 operations to factor these kind of numbers, and that is going to be way too much. So and it would take actually like millions and millions of years. So it would just not be possible or not be feasible to do this, to do it on a classical computer. Now, if we actually use a quantum computer, you can see the operations are so low. But how does a quantum computer factor this? So for that, we're going to have to look at, oh my gosh, so for that, we're going to have to look at Shor's algorithm. Right here, also. Wait. For a classical computer, for a quantum computer to achieve this 2000 to 4000 goal, it needs to have almost 10 million physical qubit. And if you see here, there'll be a picture, like somewhere here, I guess, or here. I'll have a graphic right here to come in post. It will basically show what kind of computer resources are available for free for IBM. You can get from 150. What? Sorry. You can get from 156 at the max and all the way down to 120 and like 127. So those are free. You can get them from IBM at any time. Now, how does a quantum computer achieve such low operations? Well, for that, we can use Shor's algorithm. And this part will use, This part will use quantum gates. So if you haven't checked it out right now, I highly recommend you check it. I think a card will come right here. If I'm wrong, it'll be here, but it'll probably be here. It'll just say like, hey, click on me quantum gates. Something like this will pop up. Click on it, you can watch that video. Okay, now let's get into ours. Oh, let's get not into RSA, let's get into Shor's. So here we have one register. So it's basically 2L qubits in this. So this is made up of 2L qubits. And this is also made of 2L qubits. It's a different 2L, it's a different set, but both of these contain 2L number of qubits inside. Now on the first one, we put a Hadamard gate, and as you know, Hadamard turns everything into a superposition. So you can represent it like this, or like this. That's basically the superposition of every state possible in those 2L qubits. And we only do it for the first register. Then we do a unitary operation. Not just any regular unitary operation, it does the function a to the power of x mod n. And it does it on the second register, this register, right here. Now, you can see here, fx, which is a to the power of x mod n. Then, to make that data actually usable, we do a quantum Fourier transform. And we measure the first register only. Now, just after we get, it's not like we immediately get the results. We need to do some classical post-processing. So let's get started. So this is classical post-processing. You can see here that this is data which I got from IBM when I did Shor's algorithm for 15. This is actual data. You can see there's 4 main spikes right here. 4 spikes. The rest is just noise. We can ignore that. So you don't need to look at. You can see there's 4 spikes. So what we do, we take those 4 spikes. You can see high frequency bit strings. We take those 4 because IBM gives it in binary. So convert it into decimal. That's the first step. Next, we find something called the period. The period is the spike divided by 2L, and now that's a fractional form. We simplify it and take the denominator. That's now we call it R. If it's 0 or it's odd, then we go back, find a new period, find a new R. If it isn't, then we find the greatest common divisor of a to the power of r by 2 plus minus 1 and n. And we do one time for plus, so one time it's done plus, the other time we just do minus. So we have 2 numbers, and those 2 numbers are the factor. If they are trivial, like if you try to factor 15 and you get 1 and 15, you weren't really getting anything, those are trivial. So if they are trivial, we need to find a new pair, new R, boom. If they're not, ding ding ding, we got the factors. And I actually have the code which I run on IBM. You can download the code directly from IBM, or if you want to use the results which I got on a real quantum computer, I have it in GitHub, which I will show right now as I sit down. So this is Shor's algorithm on a quantum computer.ipynb. And yes. So this is what I ran. You can see all of the had mods, and then you have the 2 mod functions. Then you have the quantum Fourier transform, and this is for 15, by the way. And if you see, if I run it with a simulator, this is a simulator. You get the 4 spikes, just the 4 that we need. But once you actually run it on a real quantum computer, you will get noise. So you can see, this is all the noise that's there. This is all the noise. Now we use this code to just keep the 4 spikes. So there's 1, 2, 3, 4. So we just take those 4. And this is the actual post-processing step. I'll focus on the results. So first one we got phase is 0.75. Denominator 4, and the factor was found as 3. Next, phase was 0, so it retried. Then phase was 0.25, and the denominator was 2. That was a trivial factor, so we retried. Next, phase was 0.25, and r was 4, and it was found as 3. So we can factor 15 on a quantum computer. Okay, so now that's the classical post-processing step. But you can actually also do Shor's algorithm on a classical computer. It's kind of like the same algorithm, but it's not like the actual quantum circuit. We're just doing a simulation of a classical, basically Shor's on a classical computer, you could kind of say. And you can see I can factor easy numbers like 121 or 131 or, wait, no, not this one. Sorry. So you can factor numbers like, if you change the mode to 0, it will do this one. Okay, so if we factor 121 using Shor's, you can see it got pretty quick. If I use 131, it will fail because that's prime, and any prime number will fail. If I put blah 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 number like this, yeah, so sometimes it'll fail, sometimes it won't, like that. And this number, it will factor pretty easily. And if I have another number like it will fail. But there are other classical algorithms that are faster than Shor's on a classical computer. So if I change detailed equal to 3, you can change this yourself. And if I run the same number again, you can see it will take around 5 to 20 seconds. Yep, you can see it factored it. But for RSA type numbers like RSA 100, even the fastest, which I think is called GNFS, like RSA 100, which is not even close, we usually use RSA 248, but RSA 100 is going to take like weeks to factor on like laptops, and it'll take 3 days to factor on some machines. So like RSA codes are pretty hard to break. So this is Shor's on a classical computer. Now let's get straight back. Well, now that we know that RSA is not secure, how are we supposed to protect our data? Well, for that, we can use post-quantum cryptography. It's a new era of cryptography, which protects against quantum computer. And the National Institute of Standards and Technology, or NIST, has done some Federal Information Processing Standards, and also known as FIPS. FIPS 203, which is MLChem or crystals Kyber. FIPS 204, which is MLDSA or crystals dilithium. And FIPS 205, which is SLHDSA, also known as Sphinx Plus. So you can see here, and companies have already started using them, and some have done on the software end, some will have done in the hardware end. So you can see these are in software, these are in hardware. The software ones are Signal, WhatsApp, Apple iMessage, Google, Facebook, LinkedIn, and the blockchain. Those are implementing or starting to implement to PQC. Some hardware like the IBM Z16. The IBM Z16 is one of the first chips with a PQC module built into the hardware, like in the semiconductor. It is built in. There's a module for PQC. The Qualcomm Snapdragon 8 Elite, the Apple A18 and A19, and the Google Tensor G5, they have an NPU, which does PQC faster than a regular CPU, but do not have a dedicated PQC module. And also, the IBM Z16 is not commercially available. So the first commercially available chip which has PQC built into it will win the race. Now, you may be thinking that, oh, why are we implementing PQC already? It's 10 million qubits. There's no reason to be scared. Like, our data is going to be safe for a long time. Right now we only have 100. 10 million is a lot, right? Well, researchers are estimating by 2033 to 2035, quantum computers may emerge where RSA could be broken by 2033. That's like only less than like 10 years from now, less than a decade away. So we need to implement PQC fast, because people are using store now, decrypt later. What they're doing is they're looking at public channel and storing all the information right now. Then when quantum computers emerge with enough number of qubits, they're going to decrypt it. So they're using store now, decrypt later. So we need to start implementing PQC as soon as possible, so our data doesn't get, personal data doesn't get available to the public. Okay, right. Okay, so now let's talk about the quantum Fourier transform. But before talking about the quantum Fourier transform, we must talk about the regular Fourier transform. Now let me stand up and explain the Fourier transform. So this is the Fourier transform. What the Fourier transform does is, if I have a wave like this wave, it will tell you what sine and cos waves make it up. So it will say that, oh, this. So these are all the waves, sine and cos waves, that make up that waveform, because any waveform can be made with sine and cos waves. So how does it do that? Well, it uses something called integration. Integration is the area under the curve. Okay. So if I have a sine function, bring my keyboard. And let's say I just want it between 0 and 2 pi. And I'll just say this as okay. this is the part of the sine wave which will be integrating. And integrating basically means the area underneath the curve. So if you have, you can see this area, you can see all of this area. So that's all positive because it's up, and all of this area is negative because it's down. So if you have both of those areas, you can see that they will cancel out. So if I use integration, which I'll put right here, two pi, not 2, whatever that thing is. So you can see I get 0. But now, what if I square the sine function? So there will be no negative values. So you can see it looks like a camel's back. Have you seen the 2 humps? Looks like 2 humps. So you can see that there is no negative area now to cancel it. So we have an area, which is pi in this case. Now, what we do here is if we have sine 2x, this is where the magic comes in. Compare it. So you can see this is so you can see that the sine 2x function is basically just kind of like compressed down. The frequency is 2 times, so 2x. So you can see it's just 2 waves instead of 1 in that whole span. So what if I multiply sine 2x with our original function? This is where the magic comes in. So you can see here that if I integrate it, this area is the same as this area here. And if this area here is the same as this one. So everything cancels out and we get 0. So the frequency will have to be the same, then only we will get a result. So now let's actually do it. Let's make another function called g of x. And I'm just going to put it for sin x for now. Oh my gosh, that's not what I wanted at all. This is also not what I wanted at all. I think I'll type like this, that's better. Yeah. Now, I'm going to remove this. Bye-bye. Also, turn this off. The first. So now, let's choose a function. So, which I'm going to apply the quantum Fourier transform. So, the regular Fourier transform for. And you can do for sine and cos both. Let's see. So here also. Okay, so let's say we have this function and oops, looks pretty random. Now, how will the Fourier transform say that, oh, it's made of this, 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 this? So that's what we're going to do right now. Wow, 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 wow. Also this whole thing. So you can see here, what I get from here is the amplitude of this in the sine wave. So if I put sine x and it gives me the output 4, it must mean that it's 4 sine x is there in the function. Now, let's change this from sine x to sine 2x. Nothing. Sine 3x, 3. So that must mean plus 3 sine 3x. Now you can see it's kind of getting that shape, but not exactly. So we gotta do more. Sine 4x, nothing. 5, no. 6, no. 7, no. 8, no. 9, no. 10, no. And I'm only going up to 10 because this is just a demonstration. Cos, there is 1. So cos x. You can see it's kind of getting that shape. Okay. Cos 2. Yes, there is cos 2. 4 cos 2x. It's getting very close now. Cos 3x, nothing. Cos 4x, nothing. Cos 5x, minus 2. So we do minus 2 cos 5x. And you can see we get that exact function. So just by changing this value and using the Fourier transform, we never had to look at any of this to figure out what the function was. All we needed was that function input and output values and a little bit of integration. And we get it. You can see this is exact. This is the from 0 to 2 pi, you can see it makes the whole function. It's the same. Now, this is how the Fourier transform works. And here, right now, I had to do sine and cos separately. So, normally, what we would do is you'd use e to the power of I theta, which is equal to cos theta plus I sine theta. So we can do both at once. You can see here that I have done the Fourier transform for this function. So you can see I just did for this function, and the x direction is the frequency, y is the amplitude, and all the blue dots mean cos, all the purple dots mean sine. So you can see frequency 1, amplitude 1, there is a sine wave. Frequency 2, nothing. Frequency 3, amplitude 4, sine wave. Frequency 4, amplitude 1, cos wave. So this is, you can see here, I basically just automated it, kinda. So all I just did was I just put in each value, and I got it just through integration. Now in real life, you wouldn't get a smooth curve you can integrate like this. You would rather just get like a series of points. So instead of getting this function, you would get something like this. Like, how are you supposed to find the area of that? Well, what we do here, find the difference. That's the difference behind the height. Now we can make a rectangle. We keep on doing that. And we make rectangles. Or let's say I'll just take a couple points so it'll be easier for me to show what I'm talking about. They aren't evenly spaced, but I'm just taking them. So you can see we find the height and difference. Rectangle. 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 So we can find the areas using rectangles, and what we can do, you can use the summation function. So this is called the discrete Fourier transform. If you give a list of points and it gives frequency and amplitude, that's the discrete Fourier transform. And I've done it here. So you can see here, all of the orange points is what I gave, and the purple points is my output. And I can change this actually right now. Wait a minute, functions, give me the actual function. Yes, this is the one. So let's say I make this instead of all this. Sine x plus 2 sine 3x 3 sine 2x. So you can see this, it looks like a curve, but it's actually just a list of points. And I'm giving that list of points, and you can see 1, 0.9. So basically 1, 2, 2.9, so 3, 3, 1.9, so 2. You can see this is the exact values which I just put in. So it works. So what we're doing here, we give it points. Here are your points. Then we put it through the discrete Fourier transform, or DFT. And then we get the frequencies with amplitudes. And this is called a linear transformation. And any linear transformation can be represented as a matrix. So this is the discrete Fourier transform matrix. But any quantum gate is also a matrix. It's a unitary operation. So instead of putting it a list of points, what if we put a quantum state in? And then we get a quantum state out. Well, that is the quantum Fourier transform. You can see here, it's the same matrix. This is the same matrix. And this is all the QFT which is going on. Now I'll get to my code and I'll actually explain, because I have QFT in my code as well. So let me just sit down. So go here, QFT. So if I run this, blink, so it'll ask how many qubit, how many it should be. So let's say I put 3, it'll make a 3 qubit quantum Fourier transform. 10 qubit quantum Fourier transform. There is always one pattern. It uses Hadamard gates and phase rotations, and at the end it uses C-swap gates. So that's all the quantum Fourier transform does. Phase rotations, Hadamards, and C-swap. Not C-swap, swap gates at the end. Now, when you're actually making a circuit, it'll be pretty annoying to see all of this stuff just there. So when you actually make a circuit with this, like how I did in my Shor's algorithm, it just makes a long bar. But I actually want to see what's inside. So I use the decompose function so I can see. And you can see here. Yeah. So now what have we learned today? We have learned how cryptography enables secure communication over public channels relying on mathematics rather than secrecy. We learned why RSA encryption is secure for classical computers. We learned that quantum computer changes this assumption. We learned how the quantum Fourier transform, we learned how the Shor's algorithm can break RSA. We learned why post-quantum cryptography needs to be implemented fast. And finally, we learned about the quantum Fourier transform. So, see you guys in the next video. Some videos will pop up. Hope you check out those. Okay, bye guys. See you in the next one.